So good afternoon everyone. Back to the class on MMM on fifth module. So in the last session we were dealing about the strain measurements, right? We dealt different instruments used to measure the strain, the classification of it, and also we went on related to electrical strain gauges, its classification based on bonded and unbonded method, and the last part of its classification, piezo-resistive strain gauges, were left out. Right, so today we'll start up with the remaining part of our strain measurement part of fifth module. So I will just share the screen, just a second. Hope the screen is visible, Tarun.
Yes.
Yeah. So hopefully no need to brush up, I feel so. So related to the strain measurements, we have done what do you mean by strain, strain measurements, classifications, advantages, disadvantages, right? All these are done. Then we dealt about specifically on electrical strain gauges. We went on with respect to its classifications as well. And in your syllabus, you have in-depth description for electrical type of resistance strain gauges. So we went on related to what you mean by electrical strain gauges, how does it look, how it operates, what are its classifications. So in that we were held up with the last type of classification, so which is nothing but our semiconductor or piezo-resistive strain gauge, right? So this part we have to now deal about. So we have dealt about how the structure looks like in unbonded type, how it is operated, and with respect to bonded type, we had two classification. One is the wire and the foil method. So that also we discussed. So this is the foil type which is done. So now we have to focus on semiconductor gauge, or it is also called as piezo-resistive strain gauge. If it is a piezoelectric, it becomes a dielectric material. If it is a piezo-resistive, it comes into the category of semiconductor. Okay, so hence the name dual, either semiconductor or it is called as piezo-resistive. So piezo-resistive and piezoelectric, both are different. It comes into two huge classification, which is semiconductor and dielectric. So here we are just focusing on piezo-resistive strain gauge, which is also called as semiconductor strain gauge. Okay, so these piezo-resistive strain gauge or the semiconductor gauge are usually formed by having etched out from the single crystals of either silicon or germanium. So both silicon or the germanium are semiconductor materials. So these are etched out through single crystal of silicon. Okay, so it helps in getting the piezo-resistive strain gauge in the form of thin films. If you want in the form of thin films, then you etch out from the single crystal. Okay, so if it is in bulk, if it is multi-lattice structured, then it will not be a single crystal, single orientation of the lattice will not be available in that case. Since it is a single structure, we are focusing here the semiconductor gauges of thin film or foil kind of structure. So it is combined with exact amount of impurities during framing out semiconductor gauges. Why? Because it needs the impurities such as boron in order to get the desirable characteristics. So usually while developing the semiconductor gauge, the amount of quantity of the single crystal of silicon or germanium you are adding, the same amount of impurity such as boron is embedded with either silicon or germanium. Then only it helps you to get the desirable characteristics. So this impurity, if the better word to call on than that of impurity is the dopant. So the reinforcement of any foreign material into the existing material will come into the picture for bifurcation related to the word impurity. Okay, so you can add on the name either reinforcement or an dopant. So when you dope some extra material to the existing silicon or germanium, it helps to get the desirable characteristics which was needed as a functionable variable for semiconductor gauges. So here, after you understand through what material it is made, so then you have to come to understand how the change of current takes place in the semiconductor gauge. So these gauges is bonded to a member which is strained. So these semiconductor gauges what you use will be embedded to an member element which is already strained. So due to this strained member, it will result in the change of current in the semiconductor material what you are using. Okay, so the advantage of semiconductor gauges is that it can even sense a very strain sensitivity. Even a very small amount of strain could be sensed, and as a result it provides the values to the higher accuracy. Even the minimum to the maximum amount of strain can be sensed, and it can deliver the value very accurately and precisely, because these semiconducting materials have the functional property of high strain sensitivity, and hence people go on with either silicon or germanium if you need a semiconductor gauge. So a gauge whose electrical resistance increases in response to tensile strain is obviously called as an p-type semiconductor. So what do you mean by this? So you will be having a semiconductor gauge. It could be either an p-type or an n-type. So if the semiconductor gauge is providing a good response to tensile strain, then it is an positive type of semiconductor gauge, so which we call in short as p-type semiconductor. On the other hand, if the resistance decreases, right, in response to the tensile strain embedded into the element, then it is a negative type of semiconductor gauge it is called. So you should be knowing the difference between the p-type semiconductor gauge and the n-type semiconductor. So if the resistance drop out due to the reduction in the tensile strain, then it is n-type, and if the resistance shoot up due to the response of the tensile strain, then we call that as our p-type semiconductor. Right, so this is a sketch of a semiconductor strain gauge. How does it look like? Okay, so you'll be having an housing of baking thing in which the semiconductor element will be embedded. So at the end, you will be having an copper lead wire, because this gauge has to be again connected to the circuitry bridge, right? For that, always we need the lead wire. So here the lead wire is being used, made by and copper. So there will be some configurations related to the dimensions what we have to use. So usually a semiconductor gauge consists of a rectangular filament, as I shown you in the figure. So you'll be having a rectangular filament of semiconducting gauge, which could be made by using either boron or germanium, right? So how about the area? So it will be having 0.05 mm thickness and 0.25 mm wide. So this is the specification what it has to follow for our semiconductor gauge of rectangular filament in nature. And along with it, the length of the semiconductor gauge can vary from 1.5 to 12 mm. So it could be either 1.5 or 12 mm based on the requirement and the functionality characteristics. You can vary the length of the semiconductors. Means you can select the semiconductor strain gauge of different lengths as per the requirement. And usually these semiconductor strain gauges are made as thin as possible. Usually these gauges comes in thin film fabrications only. It will be so thin in microns. A good packaging will be provided in order to handle the semiconductor strain gauges. Why? Because the stress of the material will shoot up with the reduced cross-sectional area. If you have pellet kind of semiconductor gauges with huge cross-sectional area, then the amount of stress which is induced in the material will not be very much. But when you have a very thin material of semiconductor strain gauge, you will be having a good amount of stress induced in the material, and hence it is always preferable to go as thin as possible in micron thickness. It is very much feasible, and it is not feasible to go in bulk or in pellet kind of thing for devising a semiconductor strain gauge. And due to this thin thickness, the gauge can be bent to the smaller radius of curvature without any fracture. So these Semiconducting materials are flexible and it could be bent to the smallest radius of curvature without any fracture because it is not brittle in nature. So this is one of the character of semiconducting strain gauge. And also these gauges are very much suitable for high temperature coefficient of resistance. So you can use this even at high temperature measurement of coefficient of resistance. So these are the important characteristics of an semiconductor strain gauge and how does it look and how it is being operated. So apart from that, there are few disadvantages we have to speak about. So these are very few. The first one is the output of the gauge is non-linear with strain. Means the output what you get from the gauge is a non-linear characteristic curve. So the response for the strain what you get in the output electrical signal is not varying linearly. It is non-linear. It could be even in the exponential way. So it depends how the output is revealed for the given input strain. So this is one disadvantage, saying that it is not linearly variable. And third, a second one is the strain sensitivity is dependent on temperature. So you cannot say the sensitivity of the strain what you're getting at room temperature will be same to that of the sensitivity of the strain what you get as the temperature increases, because it is directly dependent upon the temperature of the external temperature where you are keeping the device, and hence the strain factor is not an independent variable, it is a dependent variable in case of semiconductor strain gauges. This is also one of the drawback, because when you use this type of strain gauges you should be aware like what is the room temperature, what is the temperature enhancement. So with the increase of temperature you're getting variation in the strain, so what will be the optimized temperature at the room temperature. So all those things comes into picture because it is not independent of the temperature. So this is one of the disadvantage. Next is it is more fragile in nature than the corresponding wire or foil element. So we dealt about the strain gauges with wire bonded and strain gauges with foil also. So out of this wire and the foil element was more better. But in comparison to these two, these strain gauges are more fragile than these two. Okay, and the last part of it is more expensive than ordinary metallic gauges. So the gauges what we have dealt about until now. So it is expensive than those of the gauges, metallic gauges which are wire and the foil element one. So these are the drawbacks associated with our semiconductor strain gauges. After knowing about the concept of semiconductor strain gauges, you should understand how the preparation and mounting of a strain gauge actually takes place in preparation of the strain gauge device. So what are the steps to be followed? So we have few steps. One has to follow strictly and to abide to the rules and regulations of the procedure so that you get an good packaged strain gauge device. Okay, so what is the first step is the surface on which the strain gauge has to be mounted should be cleaned properly. Okay, the surface on which the strain gauge, you know, the strain gauge would be embedded on a movable platform, or it could be embedded on a foil, or it could be embedded on wire, the wire or the foil method you have studied. So the surface on which the strain gauge has to be embedded or mounted has to be cleaned properly. Okay, so second, if you have any traces of grease or oil on the surface, it should be cleaned by using acetone. So this acetone helps in clearing any type of grease or oil or any type of impurities which are present on the surface on which the strain gauge has to be mounted, because it should not create information of any voids or any kind of impurities embedded between the surface and the strain gauge. If that is so, a proper adhesion or bonding will not take place. And as a result, you have to see that it is also cleaned by using acetone. Next point is the surface of the strain gauge coming in contact with the test item should also be free from grease. So one thing, you have to clean up the surface and you have to clean up the strain gauge surface also which is coming in contact with the surface. Both should be free from grease. Okay, so you will do the same process for the surface on which the strain gauge has to be bonded and the strain gauge surface which has to be bonded with that of the surface. So the same process will be carried out for both the surface which will come in contact, and then sufficient quantity of cement is applied to the clean surface and the clean gauge is then simply placed on it. I told that we use the cement layer as a dielectric, as an insulating material. So once these two surfaces are cleaned, then a sufficient quantity of cement will be applied to the clean surface. First, you will clean the surface on which the strain gauge has to be mounted. So before mounting the strain gauge, you will place a sufficient thickness quantity of the cement on the clean surface, and the clean gauge is simply placed on it. So once you put a layer of cement, a layer on the clean surface, you will place the clean gauge on the surface of the cement which has been applied. Then the gauges are then allowed to set for at least 8 to 10 hours. So this process entirely has to be done before the strain gauge has to be used. So it takes a time of around 8 to 10 hours. Sometimes it takes around 12 hours also, depending upon the thickness of the cement layer, what you have added on the surface. So where the gauge has to be placed. So all these thickness of the quantity of the cement needed, everything will should be justified by doing the optimized route. So when you do the optimization of the quantity of the material, you'll come to know exactly which is the required quantity of thickness of the cement needed as an insulating material to damp the strain gauge, so to get high amount of strain induced in measurement purpose. Okay, so here the gauges are then allowed to set for 8 to 10 hours. This is over. And then if needed, a slight weight can be placed upon it for settling down. Just a second. Hello. Sir, ಕ್ಲಾಸಲ್ಲಿ ಇದ್ದೀನಿ. ಹೇಳಿ ಸರ್ ಪರವಾಗಿಲ್ಲ. I have picked the phone. ಹಾ ಹಾ. ಎಲ್ಲಿಗೆ? ಓಕೆ ಸರ್, ನಾನು ಈಗ 11:50 ಕ್ಲಾಸ್ ಸ್ಟಾರ್ಟ್ ಆಗಿದೆ, 12:50 ಆಗೋಗುತ್ತೆ. ಸರ್ ಟೈಮ್ ಆಗೋಗುತ್ತಲ್ಲ ಸರ್. ಹಾ, ಓಕೆ ಓಕೆ. Yeah, I'm sorry, there was an urgent call. So here then the gauges were then allowed for, yeah, setting out for 8 to 10 hours is over. And later, if for settling down, for solidification process, if any weight has to be added, so then you have to apply a small amount of weight just by keeping a sponge or rubber, any type of weight which has been needed to get the settling down of the cement along with that of our strain gauge. So once it is curing is done, okay, so this solidification and curing takes around for 8 to 10 hours. If needed, we'll add on the weight. So any weight which is essential so that you can add on, you should not apply a large amount of weight to it. So once the curing of the cement is done, the electrical continuity of the grid must be checked once. So whether there is an electrical continuity between the insulating material and the strain gauge, or else there will be a short circuit. Okay, so the electrical continuity of the grid must be checked once using the ohm meter. So once the electrical continuity is being checked, then these strain gauges, then the developed strain gauges will be connected to the bridge by using the electrical lead wires. Okay, these electrical lead wires will be connected to the strain gauge, which will be welded at the corners. So these are the some steps what we have to follow while preparing and mounting a strain gauge. So first is you will clean the surface which has to be needed for placing our strain gauge. So you will see that they are freed from grease and oil, both the strain gauge surface and the surface on which it has to be placed. And then you will add an required amount of layer of the cement on the clean surface, right? So on that you will just place the gauge, the strain gauge on it, and you will allow it to settle down for 8 to 10 hours. This is called as the curing period. And in curing period, if the weight is needed, you can add on small amount of weight, which helps in curing easily. So once it has been cured, the strain gauge is ready for the measurement. Okay, so before that you have to check the electrical continuity for the flow of electrical current without any short circuit by using ohm meter. So once this is done, then the strain gauge can be connected to the electrical circuitry board by using the electrical leads. So these are the steps or the procedure which has to be followed for preparation and mounting of an strain gauge. So then you should come to know what you mean by gauge factor. So related to this, we have studied in depth the theory part in our strain gauge experiment only, right? So we had around 1.5 hour class related to strain gauge experiment where I explained you in brief all the concept related to it. So it is nothing but like an brushing up only in the fifth module. But still let us focus. So about the gauge factor, you should know what you mean by gauge factor. I have told you already the change in resistance to that of the change in length will provide us the gauge factor. But still, the electrical resistance of a metallic conductor usually varies directly with respect to its resistivity and also the length. So resistivity, with the change in resistivity and with the change in length, there will be change in the resistivity, but it will be inversely proportional to the cross-sectional area. So we have the equation electrical resistance is equal to rho L by A. So L will be the resistivity factor, rho will be the resistivity factor, L will be the length, while A will be the cross-sectional area of the metallic conductor what you are using. So one thing you have to keep in mind, to measure the electrical resistance, always we use a metallic conductor. So in the metallic conductor, what is the resistivity factor? What is the length of the conducting material we are using? And what is the cross-sectional area of the conducting material? So based on these parameters, we evaluate the electrical resistance of the given metallic conductor. Okay, so now how this variation comes into picture. So you'll be having a crystal lattice structure of the given metallic conductor. So you know the crystal lattice is usually formed by a regular atomic pattern, and these atomic patterns are bonded together by mutual sharing of electrons, right? And as a result, when you have mutual sharing of electrons in the given crystal lattice, and when the current passes along the conductor in the form of directional motion of the electrons, then we get the flow of current in that direction. So you just consider a metallic conducting material, right? So each conducting material will be made by the atoms. So you will be having a matter which will be having different orientations of the atoms which is being arranged. So when there is a flow of current from one atom to the another, the current passes through this conductive material channel in the direction in which the current is made to flow. So the electrons will move in the given directional motion, and this flow is called to be as our electron flow. And next, the increased length and the decreased area of the gauge under tensile strength will always result in increased resistance. This we have already studied. If you have an increase in the length and decrease in the cross-sectional area due to the induced tensile strain, then obviously the resistance will increase. If the length has been compressed, then if the length has been compressed due to the tensile strain, then you will be having the reduction in the resistance. This we have studied already in electrical resistance strain gauges. The same concept has been told here again. And as a result, the gauge factor will be defined as the change in resistance to the original resistance of the conducting material to the change in length of the conducting material to that of the original length. So dr by r upon dl by l will provide us the gauge factor. And this gauge factor, we will not compute it. Actually, it will be supplied by the manufacturer, and this gauge factor usually lies between the range of 1.7 to 4. So it again depends upon the length of the gauge what we are using. We also spoke about the length of the gauge material, which varies from minimum to maximum length. So based on the length of the gauge material, even the gauge factor will keep on varying. And this gauge factor again purely depends upon the electrical resistance of the metallic conductor what we are using. So based on the variation in the electrical resistance and the variation in the length of the gauge, the gauge factor will be provided by the supplier. And this value which is supplied by the manufacturer will mainly depends upon the length of the gauge what we are using. So this is about the gauge factor. So once you are aware about the strain gauges, preparation method and gauge factor, you should also be knowing which are the methods which is being used in order to measure the strain. Okay, so usually we follow two. One is the null method and the deflection method, what we have dealt with respect to our experiments already. So we are again telling the same stories. So electrical resistance type of strain gauge usually uses a sensitive Wheatstone bridge circuit for the measurement of strain. So we have explained already what do you mean by an Wheatstone bridge circuit, which will be having four resistor arms, and how do you balance it at the null position, and when you vary one of the resistance, how the variation you get. So that is measured by using the deflection method. So all those are done. So the same thing. So in order to measure the strain, we will be here using an Wheatstone bridge circuit. So where it consists of four resistive arms with source of energy. So these resistive arms will be connected to an battery and an meter to show the readings. So as shown in the figure. So right, you have seen the sketch already. So where you have four resisting arm, it is connected to a meter with a source of energy, which is our battery, and this will be the flow of current through the resistor arm. And for balancing, we will balance and get the null position. So in that, basically, the basic principle of the bridge can be divided into two categories. One is the null method, another one is the deflection method. So what happens in case of null method? The ratio of resistance of any two adjacent arm must be equal to the ratio of resistance of the remaining two arms. So any arm you take, either R1 by R2 should be equal to R3 by R4, or R2 by R4 should be equal to R1 by R3, any ratio of the arms what you take. So then it shows a null position. Okay, so that is called as our null method. And what happens in deflection method? Suppose you have balanced the entire bridge and one of the resistance value changes. So then the bridge will not be balanced. It will be in unbalanced position. And as a result, a voltage will appear in the meter reading. Previously, in the null method, there will be no voltage value or negligible amount of voltage value, which shows that the given bridge is under balanced condition. But wherein in deflection method, due to variation of the resistance, at least in a single resistance arm, there will be no balancing part in the bridge. It will be unbalanced, and as a result, the voltage will be induced, and that voltage will be recorded in the indicator in the digital mode, or else what we call as the meter reading. So this method of measurement is known as the deflection method. So these are the two methods which are being used in order to measure the strain by using our Wheatstone bridge circuit. So next method is called as the resistance bridge arrangement. Okay, so here in case of resistance bridge arrangement, you will be having two legs of the resistance and other two will be connected here to an resistance gauge. So we will come to know what is it. So this is the sketch. How does it looks like? So here what happens is the Wheatstone bridge resistance arrangement is particularly convenient for the use of strain gauges. Why? Because it can be easily adjusted to either the null position or the deflection position or this one. deflection method, not the position. And hence, this is the most common type of method what we use to measure the strain. And also, it provides a means for effectively reducing or eliminating the temperature effects. So, due to these two plus points, the Wheatstone bridge has been used to measure the strain. Either it is null or deflection method. So as per resistance bridge arrangement, what all you consist in a circuit. So arm 1 you will be having a strain gauge, strain sensitive gauge. Arm 2 you will be having a similar gauge mounted on the unstrained material. Arm 3 and 4 will be the fixed resistors for good stability. So 3 and 4 will be the regular resistors. So strain 1. Arm 1 will be having strain sensitive gauge. So you will be having arm 1. So this is our arm 1 will be used for strain sensitive gauge. And then you will be having the arm 2. So this is arm 2. So where you will add a similar gauge mounted on an unstrained material. So this is a strain gauge which is mounted on an unstrained material. So it is not necessary that the material what you will be using is a strained one. So it is an unstrained material which has been embedded to the arm 2, whereas you will be having arm 1 with a strained gauge material. So this is strain gauge because it is being subjected to some external force. Here you can see it is a tensile force which is being subjected to. So this is a strained one and this is an unstrained one. Arm 1 is for strained, arm 2 is for unstrained. Along with that, you'll be having R3 and R4 as our resistors, which is connected to an battery source as shown in the figure. So here in case of deflection method, continuous readings are taken from one change of strain to another without rebalancing. In this resistance bridge arrangement, we won't keep on balancing in every stage because due to one strained and unstrained, there will be variation in the values and it will not be balanced, and as a result we go on with deflection method and take the readings. So this is convenient in comparison to that of the other method, but it is less accurate since the bridge output tends to non-linearity. So here the strain what you get is not varied linearly. So the output what we get is a non-linear variation what we get with respect to the strain. And as a result, it won't be very accurate readings what we get. But it is more convenient because every time there is no need of balancing it, and hence it is called as a convenient method. But since it cannot give the values with the linearly variable output signals, it is not very much accurate. And as a result, the strain is successfully increased or decreased. It keeps on varying depending upon the non-linearity factors which are associated with this kind of bridges. But in null balance method, after each successive change in strain, the bridge is rebalanced. Due to rebalancing thing, you will get more accurate and precise values at the output, which will not be varying non-linearly. Only thing is you have to rebalance in each and every step. Even though we need to rebalance, it is always better to go with null balance method as we get the accurate amount of output. Since the strain indicators are calibrated under null balance conditions, these methods always offer high accuracy while maintaining linear bridge output. So that's what I told you. So even in resistance bridge arrangement, you will be having two arms for the resistors, one arm for the strained strain gauge and the other arm for the unstrained strain gauge. Due to strained and unstrained strain gauge, you will not be having a null position, and hence you will be taking the readings of the variations in the indicator without balancing, and hence this is for the method deflection. And similarly, if you want to opt for null balance under resistance bridge, you always keep on doing the balancing part of the bridge before taking the reading, where you get more precise and accurate results, which will be varying linearly, means the strain will be varying linearly in case of null method, but whereas in case of deflection method, you will be having a non-linear variation for the strain response. So based on the requirement and based on the accuracy what you need, you can go ahead either with the null method or the deflection method, even under the case of resistance bridge arrangement. In normal Wheatstone bridge arrangement, you will be having four normal legs of the resistors R1, R2, R3, R4, whereas in case of resistance bridge arrangement, two legs of the resistors will be removed and mapped with the strain gauges, one with strained material and other one is the unstrained material. But in both the case, you can measure the output signal under null method and a deflection method. So if they ask you to explain the strain measurement methods, you have to speak about both the methods and you have to speak how it is measured under null condition and deflection condition with respect to the sketches also what you have to draw. So this is about the resistance bridge arrangement and Wheatstone bridge circuit, which are used in order to measure the strain. And then you should understand what happens in case of temperature compensations. So how it gets varied with respect to the temperature parameters. Okay. So now we have studied resistance type strain gauges. So how it is affected with respect to external temperature. One thing you have to keep in mind, resistance type strain gauges are very sensitive to the temperature changes. So any variation in the temperature will directly influence the strain gauge readings. How it varies. So these are the three factors in which it gets varied. So the first one is the gauge factor of the strain gauge is affected by temperature owing to the creep. Okay, so here, due to the creep nature of the conducting material, the temperature penetrates into the given material by the formation of creep. Okay, so due to that, there will be the variation of the strain, there will be variation in the gauge factor, which is measured by the strain gauge. So while explaining about the gauge factor, I told you that it also affects with respect to the external environment. So the strain what we are measuring is directly affected by the external environment. It is not independent of the temperature. I told you at that time only. So same has been replicated here in temperature compensation. So the second point is the resistance of the strain gauge element varies with a change in the temperature. So gauge factor also varies, the resistance also varies, and also the strains may be induced in the gauge due to the differential expansion. So even the strains which has been induced in the gauge will vary depending upon the differential expansion which is taking place on the member of the strain. So also it depends upon the strain gauge bonding material what you are using. Always the strain gauges are bonded on either the foil or the wire. So based on the bonding material you have used, I told epoxy and the glass fiber is also used. If you need only the measurement at room temperature, we go with the epoxy. If we need for temperature variable measurements, I told you in the last class, we embed the epoxy with the glass fiber. So again, it depends upon the bonding material what we are using. So based on that, even the strain gets varied with respect to the external temperature. So these are the three factors which affects the strain gauge reading due to external temperature influences. So these temperature influences can be compensated by two methods. So that is under the category of our temperature compensation. Since you know the strain is directly dependent upon the temperature, you should overcome these factors. So how do you compensate it? Since it is a parameter of the temperature, we call that to be as temperature compensation. So this temperature compensation may be compensated by two methods. One is the adjacent arm compensating gauge, and the second one is the self temperature compensation. So if they ask you to explain the compensation methods, you should tell why the compensation of the temperature is needed in the strain gauge, how it varies, and then come to the two categories and explain it beautifully. Okay, so let us start off with adjacent arm compensating gauge. Okay, so this is an sketch how an adjacent arm compensation gauge looks like. So in the previous strain gauge, we had an strained gauge here and a strain gauge for and a gauge for unstrained material. So in case of adjacent arm compensating gauge, the unstrained material will be replaced by a compensation gauge in order to overcome the effect of the external temperature, so that the strain which will be measured will not be varying with respect to temperature, and it will be independent of the temperature parameters. So to get the required output which is independent of temperature nature, we here are using a compensation gauge instead of the resistor R2, and this will be the regular one what we had, the test gauge. Okay, so the bridge arrangement is as shown in the figure as I told you. So for the balancing condition we have to check R1 by R2. So this is R1 by R2 is equal to R3 by R4. Why? Because R3 and R4 are the resistors, and this R1 will be our test gauge which has to be measured for the strain value, and R2 will be our compensation gauge. So R1 by R2 should be equal to R3 by R4. So this is for balancing condition. Okay, so then if the strain gauges in arm 1 and arm 2 are alike and mounted on the similar materials, if arm 1 and arm 2 are same type and mounted on similar materials, then this is the balancing condition what we follow. Along with this, both the gauge experiences the same resistance shift. So one thing, when you balance in this way, the first thing what we keep in mind is both arm 1 and arm 2 are mounted on the same material. If that is the case, the change in resistance, the shift in resistance caused by the temperature also remains the same. Both the gauge will experience the same resistance shift caused by the temperature change. It is not like for arm 1 the temperature change is different and for arm 2 it is different. Both will be possessing equal amount of temperature change, both arm 1 and arm 2. And also one more thing, it is clear that any change in the resistance of gauge 1 due to the temperature change is cancelled by the similar changes in the resistance of the gauge 2, because both will be having the same, since of due to the same value it gets cancelled and it becomes null, and the bridge will be balanced. As a result, always we use a compensation gauge which is made up of same material. In the previous thing when we were studying here, the regular one, you can notice resistance bridge material, bridge arrangement. Here the material was different. One was a material which was unstrained, and this was for the material which has to be tested. So both the material were different, and there is no chance for these two to get balanced and make the bridge zero. But in case of temperature compensation, to overcome the effect of temperature, we are using now the two gauges of the same material. One is for compensation. So any vice versa you get in the test gauge, you will be having the same change in the resistance here, so that both will get nullified, it gets balanced, and the compensation of the temperature effect could be overcome. So this is the reason why we use an compensation gauge in case of adjacent arm gauge pattern. And as a result, the output is unaffected by the change in the temperature. If you do not add on a compensation gauge, then the strain what you measure will keep on varying with respect to the external temperature where the device is kept. If it is at room temperature, you will get one strain value. If the temperature has been increasing in the external environment, then it keeps on varying. So you won't be having a consistent value of the strain for that particular material at all. So if this has to be overcome, so one of the method is to have an compensating gauge. So this compensating gauge will help in nullifying the variations got in the external environment, and hence the bridge becomes balanced and the variation due to the external environment could be overcome. So this is the first method, how we do the compensation of the temperature. What is the next method? In the next method is called as a self-temperature compensation. So what happens in case of self-temperature compensation? So this gauge basically should exhibit zero change of resistance with respect to change of temperature when bonded to a steel base. So suppose if you have a steel base as a substrate on which the strain gauge is bounded, in that case it will show a zero value of change in resistance with respect to temperature. Means there will be no external effect of the temperature embedded into the strain value what we are going to measure about, because we are using a steel base here as an substrate which is nothing but like an foil or a wire. So here we will be considering a conventional advanced gauge bonded to a steel base. Until now, we have studied the bonding of the strain gauges either through foil or through wire. We haven't come across with a steel base. So this steel base acts as a good substrate material in order to bond the given strain gauge. So this gauge will be well bonded to a steel base in order to overcome the external effect of the temperature. And next what you have to understand here is the coefficient of linear expansion of this alloy, because you will be embedding the gauge bonded with a steel base. So this is a combination of alloy. So here the gauge is made up of we studied the gauge material, right? So it is made up of germanium and it is embedded with an impurity called boron. So that itself is a combination of alloy, and that is now bonded with a steel base. And hence due to this combination of alloy, the coefficient of linear expansion for this alloy material will be 15 micrometer per centimeter, micrometer square per centimeter. Okay, so while the coefficient of the steel will be 12 micrometer. So this alloy is having a coefficient of 15 micrometer, whereas the coefficient of the steel base itself is 12 micrometer degree centigrade per meter. Okay. So this is for the combination what we get coefficient of linear expansion, and this is only for the steel which is 12 micrometer degree centigrade per meter. So when what happens during the rise in the temperature, the free expansion of the gauge is prevented. So when you have such a combination of the gauge with a steel base, when the temperature rises, so what happens? The free expansion of the gauge is prevented in this case. The gauge cannot expand. Why? Because the gauge is bonded to a steel material, steel base. It won't allow the gauge to expand with the increase in temperature. Regularly, what happens if you have a gauge embedded on a wire or a foil or a moving plate platform? With the increase in temperature, it helps the gauge material to expand. So due to this expansion, there will be variation in the strain what we get. But here what happens is the given gauge is embedded to a steel base. So this steel base will not prevent the gauge in expansion as the temperature increases, and hence the name self-temperature compensation. Okay, and as a result, there will be no variation in the resistance with respect to the change in the external environment, and hence the variation of the strain with respect to the temperature could be overcome. So this is told theoretically. Conversely, the thermal coefficient of the resistance of the gauge itself will be positive, and thus dr by r from this source is positive. You won't get any negative value value here for the change of resistance, because it is not expanding at all. It is not showing any response to the external environment. So the material, the device what you have developed itself is capable enough to overcome the compensation with the temperature, because the steel substrate what you use will not allow the gauge to expand, and as a result there is no experience of compression in the change in resistance. Only if you get the compression in the change in resistance, then you get the negative value. Okay, and as a result it retains the positive value of change in resistance. If these resistance changes are equal and opposite, then the change of resistance due to temperature will be zero. It get nullified and there will be compensation of the temperature. And for this type of gauges, okay, so the bonding element, if the gauge is bonded to aluminium, you would be getting an tensional force. So it depends upon which bonding material you are using. Previously, the bonding material used was steel base. If in case you do the bonding by using an aluminium base, so then the coefficient of linear expansion will be 23 micrometer per degree centimeter. So this would be an tensional force. So it depends upon the bonding material what you use. So this was the concept how the self temperature compensation could be applied. So basically the most widely used self compensated gauges are made from specially prepared selected melt alloys for use of specified materials. So there are beautiful tables available. So in order to select which type of alloy combination is needed for which type of strain gauges based upon what is your end application. So the well-defined table is there in the database actually where the people want to select this type of strain gauges. It comes out with the specifications and other details. So based on your requirement, you can select the combination of alloys to overcome the temperature compensation. So it purely depends upon the specified materials what you are going to use. It cannot be common for all the materials. So the temperature coefficient of resistance of the gauge is by suitable heat treatment. So temperature coefficient of the resistance of the gauge, you will get it by doing some annealing treatment. So this is done during the manufacturing process. So once this is done, it is matched to the coefficient of linear expansion of the material on which it has to be used. So it is a process of cross-checking. So once the alloys what you want to use to fabricate the strain gauges is selected, so you have to check what is the coefficient of resistance you're getting for the gauge at room temperature. And when the temperature goes on increasing, the strain value goes on changing. For that, we will be using different types of alloys. For that, different heat treatment has to be done during the manufacturing process. So once the heat treatment has been done during the manufacturing process, the coefficient of linear expansion of the material at different temperature level will be calculated and kept ready to be used when needed. So this is a back-end process which has to be done and kept in ready so that a user when select a particular strain gauge, you will be able to identify so which type of alloy will help in identifying which type of strain gauge and temperature parameter is needed. And you have one drawback related to this. One thing is, for physical reasons such as matching can only be ensured over a limited range of temperature. And I told you for mapping purpose, it is very difficult to map for entire range of temperature. So only the reason is matching of this type of material for different temperature is a difficult task, and hence it is limited for some range of temperature only. It cannot be used for all type of range of temperatures. You will be having a range, suppose from 0 to 200 degrees Celsius. You might be having a lower limit and an upper limit range of temperature for which you can have the data of that particular strain gauge, how the strain varies with respect to these factors of temperature, and how that could be compensated by using which type of alloy. So this amount of groundwork has to be done before a person operates and strain gauge at temperature effects. And if he doesn't want a temperature variation, and if he need a linear variation with respect to strain, he should always go up with self temperature compensation. For that, playing with alloys has to be must, and
Ma'am, your
knowing
voice
the
is cut.
data. My voice is cut. Just a second. Am I audible now? Hello. Am I audible?
Yes, ma'am.
Yes, ma'am,
Yeah.
you're audible.
Yeah. Thank you. Okay, so that is only the drawback. It cannot be restricted for a wider range, and people have to
Yes,
play
ma'am.
with the,
Now you're audible.
yeah. Thank you. And the people have to play with alloy combination, so that to know the range of temperature, how the strain varies, and which type of compensation has to be done, so that there will be no variation in the strain, and you will get a linear variation with respect to the strain induced. So this will come with respect to hands-on experience only. But this is a theoretical concept, what you can explain if they ask you the self-temperature compensation methods. So you have to explain both the methods, what I told you right away. Only the drawback here is to, oh, yeah, this is a drawback I told you, the limited range of temperature, and even that could be overcome. So to overcome these limitations, what the manufacturer usually does it, the manufacturer calibrates the selected gauge from each batch produced and supply apparent strain and temperature graphs for the use with the gauges. So what this helps is, since they have restricted range of temperature for the purpose of strain measurement, the manufacturers will calibrate this selected gauge and they provide a graph which tells you the variation of the strain with respect to the temperature. So the people who want to use will be knowing what is the strain value, how it is varying with respect to all the range of temperatures, so that here they can come to know where the strain value is being varied at which particular range of temperature. In this, there will be no restriction in the range, because they provide the graph for the entire range of temperature, right from 0 to that of the higher temperature the material can withstand to. So it depends upon the melting point of the material what you are using basically. Yes, so it is 12:50. So this is a simple typical graph what an manufacturer can give you, so which varies with the strain values and the temperature. So how the strain is varying with respect to temperature. So when you can refer this graph and do the experiments and you get the value, so you can cross check the strain value what you're getting at that particular temperature, is it mapping with that of the graph given by the manufacturer or the supplier or not. Then you will come to know whether the readings what you're getting is right, accurate, or the equipment has to be calibrated again before using. So all these you can think about and analyze. So when you do work on hands-on, so you will be more familiar. So this is about the compensation method. So from the next class, we will start up with the temperature measurements. So temperature measurements is the last part of the module 5. So if we cover that for around 3 to 4 hours, so we can complete our syllabus. So that's what, this is the self temperature compensation. I have explained you already. So other method was arm compensation. So under temperature compensation, we have two methods, adjacent arm compensation and the self temperature compensation. So you should explain both. So before explaining, you should tell what is the reason for temperature compensation, why it is needed. Then you have to start with a neat diagram and explain both the methods. So this ends the half section of your module 5. And in the next class, we start up with the temperature measurements. So if you have any doubts, you can ask. I hope everyone have written. I can see just the 48 numbers over here. Anyone else who haven't written your USN number, name? If anyone have not written, kindly add on. So we will meet by 2 o'clock again to have a discussion related to our practicals, lab internals, which has to be carried out.
Ma'am, that's for B2 batch or for all the batches?
See, I have done it for B3 batch. If other batch students are free, because yesterday Tarun was telling Madhu sir is taking some online class for his practical, basically for B2. Is it so?
Yes, ma'am, he's taking.
Yes, that's why I just focused on B3 batch currently. If anyone is free, you can come in to the class. It is not like one restricted only for B3 batch. Anyhow, I will upload the video recordings also. It's left up to you. If anyone is free, you can kindly join in.
Okay, ma'am.
Yeah, thank you.
Thank you, ma'am.
Yeah, yeah, bye bye. Take care.